Have you ever wondered where the universe gets its energy from? Or why stars, including our sun, shine so brightly? In the vast expanse of the cosmos, stars twinkle like glitter scattered across a dark canvas. Each one is a beacon of light, churning out an unfathomable amount of energy. For centuries, the source of this energy remained a mystery, a riddle written in the stars. But not anymore. The answer lies in a process called nuclear fusion. Now you might be thinking, nuclear? That sounds like something straight out of a science fiction movie. But rest assured, nuclear fusion is very real, and it's happening right now in every star you see in the night sky, including our very own sun. So what exactly is nuclear fusion? Picture two lighter atomic nuclei, a bit like two dancers waltzing their way towards each other. When they get close enough, they combine, forming a new, heavier nucleus. This isn't just a simple change of partners, though. This dance is one of the most powerful in existence, as it releases a tremendous amount of energy. This is the same energy that powers the stars, making them shine so brightly. It's the same energy that has been keeping our sun burning for over 4.5 billion years. It's the same energy that lights up our night sky with a spectacle of twinkling stars. And it's not just about the light show. This energy, produced by nuclear fusion, is also responsible for almost all the naturally occurring elements in the universe. That's right, everything from the oxygen we breathe to the carbon in our bodies and even the gold in your jewelry all come from this cosmic dance of atomic nuclei. So, the next time you gaze at the stars, remember, they are not just twinkling lights, but powerhouses performing nuclear fusion. Now, you may be wondering, how does nuclear fusion happen? Well, let's dive into the steps of this fascinating process. First off, let's set the stage. We are in the core of a star, where the conditions are extreme. The temperatures here are unimaginably high. Think millions of degrees, and the pressure is immense. It's under these extreme conditions that the first step of nuclear fusion takes place. Now, imagine trillions of tiny particles, all buzzing around at incredible speeds. These are hydrogen atoms, the most abundant element in the universe and the primary fuel for our star. They are moving so quickly because of the high temperature, and this speed is crucial for what happens next. You see, hydrogen atoms, like all atoms, are a bit antisocial. They have a natural tendency to repel each other due to their similar positive charges. But under the intense heat and pressure in the star's core, these atoms are moving so fast that they can overcome this natural repulsion. This is the second step in the process of nuclear fusion. As these hydrogen atoms collide at high speeds, something extraordinary happens. They fuse together to form a helium atom, a process known as fusion. But the helium atom is slightly lighter than the combined mass of the two hydrogen atoms that created it. So, where did the extra mass go? Well, this is where Einstein's famous equation, E=mc2, comes into play. That lost mass hasn't vanished. It's been converted into energy. This energy is released in the form of light and heat, which is what makes stars shine brightly in the night sky. This is the third and perhaps the most exciting step in the process of nuclear fusion. So to recap, the process of nuclear fusion involves three key steps. First, the high temperature and pressure in the star's core cause hydrogen atoms to move at high speeds. Second, these atoms collide and overcome their natural repulsion. Finally, in the collision, they fuse to form a helium atom, releasing energy in the process. This process repeats countless times every second in every star across the universe, including our own sun. It's the energy released from these countless reactions that powers the sun and, by extension, all life on Earth. And that, in simple terms, is how nuclear fusion happens. The process may seem complex, but it's really just a dance of atoms, choreographed by the laws of physics. It's a dance that's been going on for billions of years and will continue for billions more, lighting up the universe one star at a time. So why is nuclear fusion so important in stars? Well, let's dive right in. The significance of nuclear fusion in stars cannot be overstated. It's the powerhouse, the engine that keeps a star shining bright. This process, where lighter atomic nuclei combine to form a heavier nucleus, is vital in maintaining a star's stability. It's a delicate balance, really. The outward push of energy from nuclear fusion counteracts the inward pull of gravity, maintaining the star's size and preventing it from collapsing onto itself. But there's more to it. This nuclear fusion process also results in the emission of light and heat. It's what makes stars, well, stars. This light and heat radiate out into space, reaching even our own planet Earth, billions of kilometers away. Without it, our world would be a cold, dark, and lifeless place. But wait, there's still more. This isn't just about making stars shine and keeping Earth warm. Nuclear fusion also plays a crucial role in the creation of heavier elements. You see, in the extreme heat and pressure at the heart of a star, hydrogen nuclei fuse to form helium. As the star ages and the hydrogen supply dwindles, helium and other heavier elements start fusing together. This process continues, creating an array of elements all the way up to iron. And it doesn't stop there. When the most massive stars explode in spectacular supernovae, the conditions become ripe for creating even heavier elements like gold and uranium. These elements eventually find their way into new stars, planets, and yes, even us. Every atom in your body, from the calcium in your bones to the iron in your blood, was once part of a star undergoing nuclear fusion. In essence, nuclear fusion is the heartbeat of a star, and without it, the universe as we know it would not exist. To wrap up, let's review the key points about nuclear fusion. We've journeyed deep into the cosmos and found that this incredible process is the heart of the stars, the universe's energy secret. It's a cosmic dance of atomic nuclei where two lighter ones melt together to form a heavier nucleus. This process doesn't just happen anywhere, though. It requires the high temperature and pressure conditions found in the heart of a star. Much like the mighty forge of a blacksmith shaping raw metal into a useful tool. But this is not just a mere scientific curiosity. No, nuclear fusion is the linchpin of a star's stability and its radiant glow. It's the engine that powers the sun, allowing it to burn so brightly for billions of years. It's the light show that paints our night sky with twinkling stars. It's the warmth that allows life on our planet to thrive. Without nuclear fusion, our universe would be a dark and cold place indeed. Yet the significance of nuclear fusion goes beyond just making stars shine. This process is also a cosmic factory, a stellar foundry, if you will, churning out heavier elements necessary for life. Every atom in your body, the air you breathe, the food you eat, the ground you walk on, they all have their origin in the heart of stars, in the fiery crucible of nuclear fusion. So, in essence, we owe our very existence to nuclear fusion. It's the process that fuels the stars, creates the elements, and gives life to the universe. It's a testament to the intricate beauty of nature, where the smallest particles can power the largest celestial bodies. So, nuclear fusion, in all its complexity, is the simple answer to why stars shine and why we exist. Isn't that fascinating?